Yeah, thank you very much for giving me this opportunity to present a research project of ours. You said, Daniel, design manager. It's an interesting thing. What am I doing on a daily basis? Yeah, I work for Skanska, and I'm a design manager, and I'm a bridge engineer. So now we are moving to a completely different area. Being a design manager, we should remember that bridges in Sweden, they are built under design-build contracts, normally at fixed price. And so we design them and we build them. And that design then becomes very critical for the result of the project. And design manager has to check that, for example, contract requirements are fulfilled. That's the number one. But we also have to design for efficient construction and a safe construction. And on top of that, of course, design to cost. So that's my job, to prepare plans and drawings, models today for the guys that are building. That's my job. But I'm not going to talk about bridges today. I'm going to talk about robots. Now let's see, switching is here. Yeah, first Skanska. For you that don't know about Skanska, it's a Swedish company founded more than 135 years ago. Today, you can see the turnover or revenue 2022, approximately 160 billion Swedish crowns, to remember. Very important because it's equivalent to 15 billion US dollars approximately. And as you can see, a big operation in the US, the Nordic countries, UK and East Europe. All right. The project that I'm going to talk about is, we called it automated construction, and reinforcement is the subtitle. And we have been focusing on job site automation. It was initiated by Skanska and ABB in 2014. ABB Robotics, to be more precise. And the Swedish company Husqvarna joined later in this process. We tried to form a team with a deep know-how within construction and robotics. These two industries, they never meet. So we really needed deep knowledge, deep know-how in what is going on in construction and what is going on in robotics. Also, we realized that senior researchers were necessary to have in this team. And there were three different areas that we identified important. Robotics and construction, of course, but mathematics, because it turned out to be the most important part of this. We ran a PhD project in parallel to this, and that gave us the necessary connection to academia to be able to First of all, of course, have a PhD student and to document the whole thing. Financing, Skanska, ABB and Husqvarna, of course, and then Vinnova, Sweden's innovation agency, the Swedish Transport Administration, and SBUF, which is the development fund of the Swedish construction industry. The PhD project was financed by Swedish Knowledge Foundation and SBUF. Okay, now let's look at what this is all about. The background for this project was more efficient construction. We have heard here today everything is focused on more efficient construction. We don't, in heavy civil, we don't have the opportunity to use modular construction like you do in buildings. All the structures that we build, they are site-specific, designed for site conditions, and they are built manually on the site. They are very big, very heavy, a lot of reinforcement are installed, and we wanted to achieve more efficient construction, and that's as simple as that. And the background is this project that we see here is the ring road around Stockholm, the northern part of it. And it's a tunnel, as you can see on the left-hand side. And on the right-hand side, you can see prefabrication of reinforcement units. We prefabricated nets, cages, etc., but manually on the site. And it's when you look at the right-hand side picture here, these guys are rolling out a roll of reinforcement, and that it's not just a mat that you kick out, it's 5 tons of reinforcement that they are rolling out there. So it's hard and tough work. But what we saw was prefabrication will increase speed in construction a lot. Okay. We thought about the idea of automating this process. Could that possibly be done? The proposed solution that we came up with to eliminate that manual work that we saw in the previous slide was this setup. 3 robot arms hanging in a gantry, and that gantry enables the 3 robots to move in space, both X, Y, on a horizontal plane, and also vertically in with the Z axis. And that gave us the possibility, of course, to move these bars around. And on the left-hand side, the whole idea was to have the cut and bend machine on the site, and also have the reinforcement, the rebars, on coils, as you can see on the left-hand side. So the whole setup with reinforcement on coils, cut and bend machine, and a gantry with robots to fabricate rebar cages. All right. The main question, as it turned out, was how to control this machine. It's complicated enough. Of course, you have 3 robot arms that are collaborating. They can move in space and so on. So that is, of course, complicated. But how to control it? And the if we look at the left-hand side here, we see the automotive industry. They use robots everywhere for everything. They have a high volume, very low mix, can use serial production, and they have repetitive robot movements, which makes it possible to program them. So this is done by programming of the robots, and they do this over and over again. But if we look at construction, it's the complete opposite. If we look at the reinforcement, the rebar cage, it's often just one of each of these cages in, for example, a bridge project. Just one. And then we have another one that is not the same. It will look different. So we don't have that serial production that we can see in the automotive industry. It's often just one. And that requires unique robot movements. And the only way to do this then is to calculate the robot movements. That's the only way. Because if you need to program, and it's way better just to build it manually. Okay. The conclusion here was that it's necessary to calculate the robot movements. And the question is, what kind of input do we have to do that? If we are supposed to calculate the robot movements, to fabricate the rebar cage, what is the input? Yeah, there are two types of input. Today, everything that we design, we also model it as in 3D. So there is a 3D model of the reinforcement. Okay, so that is a good input with geometry and rebar data. That is one thing. The other thing that is really important is how to build. What is really done in detail on the sites when you install reinforcement. And it can be turned into 3 different parts. Bar installation order, how to use the robot tools or the tools at the site. When it comes to rebar, it's gripping and fixing the bars. And then when it comes to the robot world, you have path planning, including collision control. Because if you think about it, you have to move the bars. That is done by humans, but now it has to be done by robots. And you build the cage, and therefore you install more and more obstacles, and you have to check that you are not colliding with all these obstacles that you are installing. So, to start with, the bar installation order is a tough problem in itself. If you think about it, a rebar cage maybe 200, 300 bars, and the number of possible installation orders is n factorial, infinite number. So you have to find the installation order, because the guys that build a cage like this, they find it up here. So you have to find it with mathematics. And that is possible. We use what is called assembly by disassembly. So disassembling the cage bar by bar, starting with repulsive potential and so on, and disassembling the cage, and there finding the installation order. And you have to check that installation order really is valid, and that you can do only with the path planning and checking that the robots really can do the work grip, tie, and so on. So, and that's why mathematics became so important for this. It's a mathematical problem, the whole thing. So, to summarize, we concluded that you have two things, digital model, and you have the information on how to build. That is what you have to develop algorithms to calculate all the robot movements. Early on in the process, we realized that we needed to test this in real life, not just only computers. So we built a lab prototype, scale 1 to 2, and you can see it here in this slide. You see one of the rebar cages that we used, and the three robots. You can see the three robots' arms, even if they are white, you can see them there with ABB sign on them. And you can also see parts of the gantry in the background. So this is a lab prototype that we built. And trying to summarize what this is all about, you can, on the left-hand side here, you can see the second cage that we used. These two cages, by the way, they are, the first one is from a bridge that we built some years ago, and this is from a tunnel project. So they are real cages, but scale 1 to 2. On the left-hand side, you see the digital model. It's a result of the work from the structural design. The structural engineer is developing this. He calculates, of course, and prepares this digital model. That I would call a standard procedure in the construction industry. This is where we are at today. What we then have done is develop algorithms that calculates all the necessary robot movements to fabricate that cage automatically. And on the right-hand side here, you can see this cage being fabricated, and now we will see later on here, I will show you a short video that shows this process going on. And the interesting thing here, as I see it, is that the designer can use the algorithms already at the design phase to check that the fabrication is okay. We never have that opportunity today. We don't even know if all the reinforcement is installed in the structures that we design. Okay, good. Last slide. Documentation. We have, in this PhD project, we have, of course, written some papers. This is one of them in automation and construction, where we detail all the whole process. So that one is documented. And we have also a small YouTube video, if I can just show a few seconds of that. Here we can see it and try to add some text, no sound. But we wanted to document that this is in fact possible to do. We see the two cages here, we call them 1 and 2. And it's just 3 minutes, but we stop here in a short one. What you can see here is this machine, I call it a machine, building these two cages. And all these robot movements, they are actually calculated, they are not programmed. So the algorithms find the installation order, calculates all these robots' movements needed to install the bars here, and in the meantime checks that there are no collisions. And we used, of course, fast forward. It doesn't go this fast. But I can tell you that robots are very fast if you want to. So we can stop it here. Thank you. And I have one final comment. And we didn't realize really what this was all about when we started it. We just wanted to see, is it possible to install reinforcement using industrial robots? And I would say the answer to that is yes, but I think there is a more important conclusion to this, and that it's that job site automation is in fact possible. And you need to have these digital models. We saw digital models here today, and I agree, they are very expensive. But the tools are getting better and better. And by using these digital models, we can achieve things like this. And we can start using machines, robots, on the sites. So, thank you.